In this example problem, we're told that we've got this negatively charged particle moving to the right with constant velocity, and then it enters a region with an electric field, a constant electric field, and we are told that it slows down. But it does not change direction. So it's not curving its path, it's just continuing along this straight line, getting slower and slower and slower. Maybe eventually it comes to a stop and turns around the other way, but it's not curving its path. And we want to know, first of all, which direction the electric field is pointing in this region. So let's take a look at this first in terms of force, because electric field is related to force. If this object is moving to the right but getting slower, what does that tell us about the force acting on it? If you have an object moving to the right and you want it to slow down, which direction should the force be? Yeah, pushing the other way. We should expect this to be experiencing a force to the left if it's in the process of slowing down. Because from Newton's laws in 7b, we know that force equals mass times acceleration. An object that's moving to the right but getting slower and slower and slower is experiencing acceleration to the left. Because if you've got, let's say, initial velocity, and then the final velocity is slower but in the same direction, the change in velocity is the difference. The delta velocity is the difference that takes you from initial to final. So this would be the delta velocity. Just the vector you have to add to the initial velocity to change it into the final velocity. And acceleration is going to be in the direction of delta velocity, because acceleration is delta velocity over delta time. So if an object is moving to the right but getting slower, then the acceleration is to the left, which tells us the force on this object is to the left. The force on this test object is to the left. And if the force on the test object is to the left, how does the force on the test object relate to the electric field in that region of space? What's that relationship between force and electric field? Yeah, we can almost go back to the electric force equals charge times the electric field. In this case, we know the force is to the left. What do we know about the charge in this case? Yeah, the charge is a negative value. So what direction does the electric field have to be if we can multiply it by a negative scalar and get a vector to the left as a result? Well, you could say it's in the positive x direction. You could also just say it's to the right. Keep in mind that vectors themselves do not have positive or negative signs. A vector is not positive or negative. A vector is just in some direction. If it's along one of the axes, we could say, for instance, it's in the positive x direction, or it's in the negative y direction or something. But the direction itself does not mean the vector is positive or negative. The vector just is some quantity in some direction. But yeah, the electric field is definitely to the right, the positive x direction, because a negative multiplier reverses the direction of a vector. So if a negative charge is experiencing a force to the left, that means it's in the presence of an electric field to the right. And we're told that this is a constant electric field, so presumably it's this same electric field everywhere, a uniform electric field. So this entire region of space just has a constant electric field to the right.
Casey?
Yeah.
When would we know when to use the point that we're looking at as like the charge, and when to just think of it as like a point when you're doing like these problems?
What do you mean as a point versus as a charge?
So like in this one, since we have like a charged particle, when would we like look at the charge and use the charge?
Well, in this case, we know something about the force acting on the charge, because we know the charged particle is moving, and we know something about how its motion is changing. The fact that the motion is changing in a certain known way tells us something about the force acting on that particle. And if you care about the force acting on that particle, you're treating that particle as the test object. Whereas if we cared about the effect this particle had on something else, then that means we're treating that particle as the source charge. But in this case, we care about what's happening to this object. So we're treating it as the test object. And also we're talking about an electric field. Presumably this electric field is caused by something else. Maybe we have, for instance, maybe there's a large positive charge over here and a large negative charge over here, creating an electric field going from the positive plate to the negative plate. But we don't actually have to care about what caused this electric field. It's enough to know that there is an electric field in this region of space. And that we know that the electric field is to the right because this negative test charge is experiencing a force to the left. And we know it's experiencing a force to the left because it's moving to the right but getting slower. Moving to the right but getting slower means it's experiencing a force to the left. Any other questions on that so far? So we know that this region of space has an electric field to the right. And also the next question in here is asking about higher or lower electric potential, that is the voltage. And what do you know about electric field vectors versus electrical potential or voltage? If you know the direction of the electric field vector, what does that tell you about voltage? Yeah, electric field vectors always point in the direction of decreasing voltage. Electric field is always going to point from the high voltage region to the low voltage region. And potential in this context just means voltage. Same different terms from the same thing. So that suggests that the region the electric field is pointing from is a high voltage zone. The region it's pointing towards is a low voltage zone. So this region is high voltage. And this region is low voltage. And note that we don't need to refer to the charged particle at all in order to do that. Ignoring the test charge, if we know the electric field is to the right, that means the left side is high voltage and the right side is low voltage, because electric field points from a high voltage zone towards a low voltage zone, the direction of decreasing voltage. So we've got the voltages here. Also, if we wanted to draw in equipotential lines, what would the equipotential lines look like in this case? If we wanted to draw all the locations that are at the same voltage.
Would they just be vertical?
Mm-hmm. Yeah, because they have to be perpendicular to the electric field vectors, and therefore they would be vertical. So for instance, if you start out at this location has a certain voltage associated with it. If you move with the electric field, you're decreasing the voltage. If you move against the electric field, you're increasing voltage. But if you move perpendicular to the electric field, the voltage does not change. So this vertical line would be an equipotential path. If you start somewhere on this line and you move along that line, you're not changing your voltage at all. Likewise, this vertical line would be an equipotential, and this one, any vertical line would be an equipotential curve. And since we're talking about a constant electric field, we would probably draw these equipotential lines evenly spaced. Like maybe each one of those represents decreasing by 5 volts, like minus 5 volts, minus 5 volts, minus 5 volts, minus 5 volts. So we might even label these. Maybe this is like 50 volts, 45 volts, 40 volts, 35 volts, 30 volts, 25 volts, decreasing by the same amount each step. And that's really because this is a constant electric field. The electric field being the same everywhere, and this goes back to the idea that delta voltage equals negative electric field times distance. If the electric field is constant, then every meter of distance corresponds to a specific drop in voltage. And that's going to be consistent. this 1 meter going forward, like let's say these are 1 meter apart. 1 meter going forward kind of corresponds to a specific drop in voltage. The next meter going forward corresponds to the same amount of decrease in voltage. And the next meter beyond that, same decrease in voltage, and so on. So the equipotential lines would be equally spaced in voltage by default, like each one of these represents another -5 volts or something. But because the electric field's constant, they're also equally spaced in distance.
So if the electric field wasn't equally spaced out from each other and they were like different in density, how would you like compare the different magnitudes?
In that case, like let's say the electric field was much, much weaker in some region. Weaker electric field, and again, we want to make sure that the delta voltages are the same from one to the next. Like you might choose when you're mapping this out to draw an equipotential line every 5 volts. Let's say you have a strong electric field so that it only takes like a couple of centimeters to go through 5 volts of voltage drop. But if the electric field is weaker as you get further out, weaker electric field means you'll need more distance to get the same voltage difference. So as the electric field gets weaker, the equipotential lines would be spaced further apart from each other. It's still the same 5 volts of difference, or whatever difference you're mapping, but it would be a further distance to get the same change.
So that's like if the lines are more shallow.
Yeah, or if they're not parallel to each other, because these parallel lines means they're the same distance apart from each other. So you're going to have the same electric field strength everywhere. But let's say instead we had a point source charge. Let's say we've got our source charge is just a single point. The electric field lines would be lines emanating outwards from there. And so your equipotential line is going to be curving to be perpendicular to all of those electric field lines. So your equipotential lines in that case would actually be circular. Every point along this circle would be the same voltage. And that would be presumably high voltage, because if you go outwards along the electric field line, you're now at a lower voltage. So every point along this circle would be at the same somewhat lower voltage. Again, the equipotential line is going to be curved because it has to be perpendicular to the electric field everywhere. So maybe we might have, let's say this is, and I'm just making up numbers here, but let's say this is like 50 volts. And maybe the next one out is 40 volts. Maybe we're going to just put in a label every 10 volts. But if this distance, that delta x, corresponds to losing 10 volts in this strength of electric field, but then we go further out the electric field is weaker. So it's going to take more distance to get the same 10 volt drop. So the next equipotential line, 30 volts, is going to be further away, maybe out here or something. And then the 20 volt curve is going to be even further out, because with a weaker electric field, it's going to take more distance to get the same 10 volt drop. Likewise, if we went further in, if this distance represents 10 volts in this strength of electric field, if we go closer, another 10 volts is going to be less distance. Maybe this curve is the 60 volt region. And then even closer still, maybe this is the 70 volt region. Getting higher and higher voltage, closer and closer together as we get to a stronger electric field. So this would be one example of a map of the equipotential lines, showing the voltage at various locations around this source charge. And one of the nice things about an equipotential map like this is that it makes it much easier to find delta voltages along some path. Like let's say you're traveling from here to here. And you wanted to figure out how much work that took. If you're traveling from here to here, if you're trying to work out work equals force times distance at every little bit of the path, you're going to have to figure out the force here times this distance plus the force here times this distance plus the force here times this distance. It's going to be a huge mess. But if you look at it in terms of voltages, you just have to care about initial voltage and final voltage, which is on the 50-volt line. So what's the change in voltage from here to here?
It's 20 volts.
If you're looking at delta voltage, all you have to care about is initial and final. From 30 to 50, final minus initial would be 20 volts. So that path, that journey is associated with 20 volts, positive 20 volts of delta voltage. And if you know the delta voltage, how do you find the change in energy? How does potential energy relate to voltage? Right, all you've got to do is multiply by the test charge. So if you had like a 3 coulomb charge and you wanted to move it along this path, you would just take 3 coulombs as the test charge, multiply by 20 volts, you get 60 joules. So that means it would take 60 joules of work to move the particle along that path. Test charge times delta voltage equals change in potential energy, which presumably would be the amount of work you'd have to do. But again, all you have to care about is the initial and final values. This is a path-independent measurement. All that matters is initial and final, the endpoints. Any questions on that so far? So let's tie that back into this situation from the original practice problem. We know we've got high voltage over here, we've got low voltage over here. So that means from initial to final, delta V is, would you say delta V is positive or negative? Yeah, it should be negative. We're going from a high voltage zone to a low voltage zone. We have lost voltage as we go from left to right. So delta V is negative. Delta V is less than 0. But we also want to consider the potential energy of this particle. To figure out the change of potential energy of this test object. And once again, how do you convert voltage into potential energy? Yeah, Q times V. We're just multiplying by Q. But what do we know about this particular charge? It's negative, right? If you multiply both sides of an inequality by a negative number, what happens to the inequality? It flips. We get a number that's greater than 0. Or to put it another way, delta V is a negative number. You multiply a negative times a negative, you get a positive. So delta potential energy is positive, which means even though we're moving to a lower voltage zone, this particle is gaining potential energy. So this path from initial to final, it involves a decrease in voltage because voltage is a property of the location, but it involves an increase in potential energy for this negatively charged particle. The particle is gaining potential energy as it moves from the high voltage zone to the low voltage zone. Because in a high voltage zone, the negative charge has low potential energy. In a low voltage zone, the negative charge has high potential energy because it's a negative charge. If we had been using a positive charge, then high voltage would mean high potential energy and low voltage would mean low potential energy. But the negative test charge reverses that. So the high voltage zone gives the negative charge low potential energy, and the low voltage zone assigns the negative charge high potential energy because we're multiplying by a negative. Any questions on that so far? So as this negatively charged particle moves through this electric field, moves along the electric field, it's gaining potential energy. But think back to conservation of energy from way back in 7A. It's gaining potential energy. We should be able to treat this as a closed system. What other type of energy is changing here? Yeah, kinetic energy. If we set up an energy interaction diagram, the electric potential energy is increasing because we've got a negative charge increasing its voltage. So presumably the kinetic energy is doing what? Yeah, kinetic energy is decreasing, corresponding to the object slowing down. Absolute value of velocity decreases. And we can treat this as a closed system because those are the only things that are changing. And the only force acting on this is from the electric field, which we're already taking into account as a potential energy. So conservation of energy alone would predict that the object is slowing down. And that's what we were expecting from the very start. At the very beginning, the problem told us this particle is slowing down as it moves. So the idea of forces and the electric field agrees with the idea of conservation of energy and the potential, the voltage. So all this stuff is consistent. It all matches up with the prediction that this object is slowing down as it moves. You just got to be very careful with the signs and the idea that a negative test charge means that high voltage is low potential energy for that object, and low voltage in space is high potential energy for that object. Because voltage is a property of the location in space, whether there's a particle there or not, but potential energy is a property of the particle, including its sign. Any other questions on that? Or any other questions on electric fields and potential in general? All right, then let's take a look at some versions of the right-hand rule for magnetic fields. Because this is going to be very important for both the magnetic field stuff and for the induced current stuff you'll probably be getting to next week as well. We briefly talked about last time what causes magnetic fields and what magnetic fields do. In general, if you want to create a magnetic field, you need a moving source charge that creates a magnetic field, usually written as capital B. And that magnetic field exerts, or is able to exert, a force on moving test charge. The motion is really the important thing here. Any charge creates an electric field. Any charge can experience a force from an electric field. But if the charge is moving, it also creates a magnetic field. And if the charge is moving, it can also experience a force from a magnetic field. The magnetic field can also exert torque on a magnetic dipole. This is how compasses work, for instance. The compass, the magnetic dipole, twitches to align itself with the existing magnetic field, which is a great way to measure a magnetic field. If you have a magnet and you have a compass, you can just put the compass near the magnet, and the direction the needle orients itself is the direction of the magnetic field at that location. But if we want to take a look at this in terms of how magnetic field interacts with moving charges, let's say you have a charge in motion. For simplicity, let's assume it's a positive charge, and we're going to treat this as the source charge, in the sense that this is a charged object, it's moving, and what we care about is the magnetic field it creates. So let's say it is moving, let's say moving to the right. And we want to figure out the magnetic field that that moving charge creates. The magnetic field is going to be different at different locations in space, but let's just pick a location to start with. Let's say we're looking at a location directly above it. What is the magnetic field here? And there are a couple of important properties to keep in mind when you're looking for a direction of a magnetic field. So the important properties are that the magnetic field is always perpendicular to the velocity of the source. If the source charge is moving to the right, that means every bit of magnetic field it creates is going to be perpendicular to that direction. However, that alone is not enough information, because perpendicular to the right might mean up, might mean down, might even mean outwards or inwards. There's infinitely, or any diagonal, there's infinitely many directions that count as perpendicular to the right. So we're going to need one more piece of information. And that is that the magnetic field is also perpendicular to the radius vector. Radius in the sense of the vector from the source to the location of interest. So this would be the radius vector here. And that narrows it down a great deal more. We've got a radius vector, we've got a velocity vector. What possible directions would be perpendicular to both the radius vector and the velocity vector?
It'd be like pointing out or in.
Right. In this case, directly outwards or directly inwards compared to the, in this case, the board itself. So that means at this location, the only possibilities for magnetic field are straight out or straight in. And as usual, when we've narrowed it down to two possibilities, the right-hand rule is used to determine which of those possibilities. And there are several variations you can use on this that are all called the first right-hand rule, or the first type of right-hand rule. So the first right-hand rule is all about this interaction here. The first right-hand rule. And one way to do this is if you put your hand at the point of interest. So you just take your right hand, ball it up into a fist or whatever, put it at the point that you care about, stretch out your fingers straight towards the source charge that's causing everything in the first place. And note that so far I can still swivel my hand around, but I want to curl my fingers in the direction the charge is moving. So again, put your hand at the point of interest, the point you care about, stretch out your fingers straight towards the source charge that's creating the effect, and swivel until you can curl your fingers in the direction the source charge is moving. And your thumb should tell you the direction of the magnetic field. So at this location, it looks like the magnetic field should be straight out of the page. And in fact, that should be true anywhere above this charge. And of course, it gets weaker as you get further away, like you should expect any field to. The further away you get from the source, the weaker the field gets. But it's going to be outwards. Any questions on that so far? Or let's say we take a look at a location under the charge. If we consider this location, again, we could draw a radius vector. And we want a new vector that's perpendicular to the radius and perpendicular to the velocity. That, again, narrows it down to outwards or inwards. So to choose outwards or inwards, we could use the same right-hand rule. Put your right hand at the point of interest, stretch your fingers straight towards the charge, and swivel until you can curl your fingers in the direction it's moving. Now your thumb tells you the direction of the magnetic field. So this would be an inwards magnetic field. And in fact, everywhere in this region below the moving charge is going to be inwards magnetic field. And the thing is, this is not a two-dimensional situation. You can do this approach anywhere outside the board as well. For instance, let's say we're talking about this location right here out of the board a little bit. At this location, the radius vector would be towards the charge. So we've got radius vector inwards, velocity vector to the right. So now this is what our arrangement looks like. We've got a radius vector towards the charge, velocity vector in the direction it's moving. What possible directions would be perpendicular to both of these vectors? Yeah, up versus down. So at this location, closer to the viewer, at this location, the magnetic field has to be either upwards or downwards. And again, you can use a right-hand rule. put your hand at the location of interest, stretch out your fingers towards the charge, and swivel until you can curl your fingers in the direction it's moving. Now my thumb's pointing down. So at this location in front of the board, the magnetic field is downwards. And we get a smooth continuum here. Magnetic field is pointing outwards, downwards, inwards, and if you go behind the board, it would be going back upwards. So these magnetic field vectors, if you connect the dots here, actually form a loop. Of course, that doesn't mean anything's moving in a loop necessarily. It's just that if you draw out all the magnetic field vectors, they form this curl, this loop around the axis of motion. So the direction of motion, the velocity vector, is going to act as the axis of symmetry for this loop of magnetic field lines. So that's going to look kind of like, if I can maybe draw this in perspective. Particle is moving like this. The magnetic field lines you get are going to look kind of like this. So you're going to get sort of this curvature around the moving charge. If you can imagine like a three-dimensional circle centered around this axis of symmetry. And if you go further ahead, you're going to get some similar magnetic field, but it's going to be weaker because you're further out and bad angle. And further back, you're going to get a weak magnetic field as well. But it's going to be mostly concentrated in the region near the particle. One other curiosity here is if you're directly in front of the particle, like if the particle is moving straight towards you, or if you're back here and the particle is moving straight away from you, the right-hand rule falls apart and you get no magnetic field. So if a charged particle is moving straight towards you or straight away from you, you don't get a magnetic field at all. You get the most magnetic field if it's currently moving right past you. Like let's say you're standing here, the particle is moving right overhead, like right past you, and you're close to it, you're going to get a strong magnetic field. This sort of curling approach, the idea that the magnetic field curls around the motion of the charge, also leads to another variation of the first right-hand rule that's often much more useful. If you curl the fingers of your right hand in the direction the magnetic field is sort of swirling, you'll find that your thumb points in the direction of the velocity vector. So this is often a much easier way, a much faster way, if you care about not just one point, but just the general swirliness of the magnetic field vector, or the technical term is the curl of the magnetic field. If you just point the thumb of your right hand in the direction of the motion of the charge, then the curvature of your fingers tells you the direction the magnetic field is circulating. So a particle moving to the right means the magnetic field is going to be curling like this, all the way around. So that's another variation of the first right-hand rule that's sometimes much more useful. Any questions on that so far? Also, this doesn't have to be like a charged object that is in motion. Like I think the most easy to visualize case is if you just take like a lump of plastic and charge it up with positive charge and throw it. What would happen if we had used negative charge instead? How do you think that would influence the result? Like if we take a negative charge particle and move it in this direction, what do you think would happen to the results? Yeah, it just becomes the exact opposite. So if you've got a positive charge moving to the right, you're going to get magnetic field curling like this, outwards from above, and then downwards closer to you, and then inwards below, and then curving upwards behind it. But if this had been a negative charge moving in the same direction, you actually get the reverse, inwards above, downwards behind, outwards underneath, and upwards in front. So a negative source charge is going to have the exact opposite effect. You can use the same right-hand rule, but just reverse the results. Or another way to do that is to treat a negative charge moving in one direction as if it's a positive charge moving in the opposite direction. Like if you've got a negative charge moving to the right, one way to deal with that is to just pretend it's a positive charge moving to the left, and everything else should work out just fine. Or another approach you could use is for negative charge, use your left hand instead. So any of those will work in terms of getting the correct directions. But also, instead of a charged object that's moving, what's another form of moving charge? What sort of moving charge were we looking at back in 7B? What do we call the motion of charge? Yeah, electrical current. So if you just have a wire that's staying still, but there's current flowing within that wire, that also technically counts as moving charge. So we can also look at the charge created by the magnetic field created by a wire with current flowing through it. For example, let's say we have a vertical wire, and let's say there's electrical current flowing, let's say, upwards. We can use the exact same right-hand rule principles, just treating upwards as the direction of motion, because that's the direction current is flowing. So instead of saying the magnetic field is perpendicular to the velocity, we're going to say magnetic field is perpendicular to the current in the wire. If you think of current as having a direction associated with it. So for instance, over here, we've got a radius vector, we've got a current. Radius and current also means in this case, the magnetic field has to be outwards or inwards. And as a shortcut, since we know that we're going to get magnetic fields sort of swirling around the wire, the only real possibilities are swirling this way or swirling this way. And you can use the other variation of the first right-hand rule, using thumb as the direction current is moving. So thumb is the current or the motion of charge, and the curvature of the fingers of your right hand give you the direction magnetic field is circulating. So magnetic field is going to be circulating like this. We're going to get this curved magnetic field. And of course, at any given point, the magnetic field is just a vector, which is a straight line direction. But the idea is that here, the magnetic field is outwards. Here, the magnetic field is to the right. Here, the magnetic field is inwards. So all those directions looked at together form this curved sort of path. So those would be the field lines, much like electric field line diagram, but it's magnetic field lines instead. Any questions on that so far? So that's the first right-hand rule. And again, there are several variations on it, but the first right-hand rule, or the first type of right-hand rule, is all about the interaction between the moving source charge or current and the magnetic field it creates. So if you know something about how the source charge is moving, you can figure out the magnetic field it creates. You can also do that in reverse. Like let's say we didn't know the current, but we knew magnetic field was circulating like this. Curl the fingers of your right hand in the direction magnetic field is curving, and your thumb tells you the direction of the current that had to cause that. The second right-hand rule is all about this interaction, the interaction between the magnetic field and the force it exerts on a moving test charge. So let's say we have an existing magnetic field. In fact, let's just use the magnetic field over on this side. Let's say we've got this inwards magnetic field. And for simplicity, let's assume that it's the same strength everywhere. So let's say the magnetic field is inwards and the same strength everywhere. And let's say we have a particle that's moving, a test charge. That is a charge that we care about the force on this charge. Let's say a positively charged particle that's moving upwards. It turns out that the force on the charged particle, the force on the test charge, also obeys some very useful perpendicular properties. First of all, the force on the test charge is going to be automatically always perpendicular to the magnetic field. And also, the force on this test charge is going to be perpendicular to the velocity of the test charge. So that also allows us to narrow it down to two possible directions. We've got magnetic field, we've got velocity. what directions could be possibly perpendicular to both of those? Yeah, in this case, left and right are the only possibilities. So that means the force on this particle is either left or right, because those are the only options perpendicular to the magnetic field and the velocity. And to narrow it down to one of those two, once again, we use a right-hand rule. For this one, again, there's multiple variations. The one I usually see is the 3-finger variant. If you can hold your thumb, index finger, and middle finger exactly like this, so sort of finger gun shape like this, and then your middle finger pointing exactly perpendicular to those. The usual way this is set up is thumb represents velocity, index finger represents magnetic field, and the middle finger represents the force. So if you point your thumb in the direction of motion and your index finger in the direction of the magnetic field, because note that I can swivel this around, but I need to be able to point my index finger in the direction of the magnetic field, and then my perpendicular middle finger tells me the direction of the force. So that'll be a force to the left. Or if you have trouble holding your fingers perpendicular, that can be kind of uncomfortable. You can also use the flat hand variant. Point your thumb in the direction of the velocity, your flat fingers in the direction of the magnetic field, and imagine the palm of your hand giving a shove to the particle. So velocity, magnetic field, force. This particle is going to experience a force to the left. And as usual, if this had been a negative charge instead, you could just work it out as normal and then reverse the final force. But the final result is reversed if it's a negative charge. So that's the second right-hand rule, describing the relationship between the existing magnetic field, presumably from some other source, and the force it exerts on a moving test charge, or a wire. A wire with current will also experience a force in the same sort of way. Any other questions on those right-hand rules for magnetic fields and magnetic forces? All right, try applying these to any practice problems you've got from FNTs or practice tests over the weekend, and we will look at some more examples next time. See you then.
Thank you.
You're welcome.
Thank you.